Now what we have to find, starting with that, now here P is less than 0. So let's say P is equal to minus QQ if Q is greater than 0. Okay. So P raised to 1 upon 3 is equal to Q raised to minus 1 raised to 1 upon 3. That is equal to Q minus Q infinity, also equal to minus Q infinity square. So X alpha plus Y beta plus 2 gamma upon X beta plus Y gamma plus 2 alpha will give, I'm replacing, so minus X cube minus Y Q gamma minus Z Q gamma square minus X cube unity minus Y cube square minus Z cube. So X unity cube Y x raised to 4 Z x raised to square upon X unity plus Y unity square plus Z. So that is X plus Y upon X infinity plus Y infinity square plus Z. When I take common, you get this as infinity square. If xn is equal to cos of pi upon 2 raised to n, which is equal to cos of pi upon 2 raised to n plus I sin pi upon 2 raised to n, then x1, x2, x3 and so on till infinity, is equal to, so cos pi by 2 plus I sin pi by 2, cos pi by 4 plus I sin pi by 4, cos pi by 8 plus I sin pi by 8 is equal to, till the extent to infinity, so cos of pi by 2 plus cos of pi by 4 plus cos pi by 8 and so on. At one side, that is your real part, plus I common, sin pi by 2 plus sin pi by 4 plus sin pi by 8 till the extent, so cos pi by 2 upon 1 minus half plus I sin pi by 2 upon 1 minus half, so cos of pi plus I sin pi, value minus 1 plus I into 0, the answer is minus 1. The three vertices of triangle are represented by the complex numbers 0, z1 and z2 if the triangle is an equilateral triangle. Okay. Now since the triangle is an equilateral triangle, I would say z1 minus 0 is equal to z2 minus z1 is equal to 0 minus z2. So z1 square is equal to z2 minus z1 square is equal to z2 square. So z1 modulus z1 bracket of z2 minus z1 modulus of z2 minus modulus of z1 is equal to z2 modulus of z2. So here z1 modulus of z1 is equal to z2 modulus of z2 So z1 upon z2 is equal to z2 upon z1. So you get as z1 minus z2 upon modulus of z2 minus z1. And z2 into modulus of z2 is equal to z2 minus z1 modulus of z2 minus modulus of z1. Therefore z2 minus z1 into z1 minus z2 upon z1 into modulus of z2. You get it from this equation. After this, z1 into z2 is equal to z2 minus z1, z1 minus z2, that is equal to z1 z2 minus z1 the whole square minus z2 the whole square plus z1 z2. So what you get is z1 z2 plus z1 z2, z1 the whole square plus z2 the whole square. So your modulus is equal to z, that is equal to, this is the answer, which is your option number C. The points z1, z2, z3, z4 in complex plane are vertices of a parallelogram taken in order of P. Now since the diagonals bisect each other and these are our points, I would say z1 plus z3 upon 2 will be equal to z2 plus z4 upon 2. So z1 plus z3 is equal to z2 plus z4. Your answer is B. The value of summation 6k is equal to 1 sine 2 pi k upon 7 minus I cos 2 pi k upon 7 is first we will write 6 times the outside, so minus I cos of 2 pi by 7 plus I sine 2 pi by 7 plus cos 4 pi by 7 plus I sine 4 pi by 7 and so on till the extent of 12 pi by 7 plus I sine 12 pi upon 7. Now here I is equal to this is your alpha, this is your alpha square, alpha cube and so on till the extent of alpha 6, because alpha is equal to cos theta plus I sine theta, so cos of 2 pi plus I sine 2 pi by 7, that is equal to I alpha raised to 6 minus 1 upon alpha minus 1. I'll open the bracket, alpha raised to 7 minus alpha upon alpha minus 1. What you get is I into 1 minus alpha upon alpha minus 1. I into minus 1, that is, this is a minus. So that is positive I. Answer is D. If W is equal to Z minus I upon 1 plus Zi raised to n is an integral, then W lies on the unit circle 4. Okay. So W is equal to Z minus I upon 1 plus Zi raised to n is equal to Z minus I upon I is Z minus I So that is 1 upon I raised to n minus I raised to n. Infinity was equal to 1. So what you get is 1 into minus I raised to n is equal to 1. So your answer for this is all n, because W lies on the circle. If x plus yi and W is equal to 1 minus zi upon z minus I, then W modulus is equal to 1, implies that in complex plane so let's say W is equal to 1 minus zi upon z minus I. So 1 minus I into x plus yi upon x plus yi minus I. Therefore, modulus is equal to 1. 1 plus y minus ix upon x plus y minus 1 is equal to 1. So 1 plus y minus xi is equal to x plus y minus 1 I. Root of a square plus b square. Your a square is 1 plus y I plus x square. So x square plus y minus 1 the whole square. Both will be in the form of a plus bi. So your r you are considering. Now equating both of them, what you get is root gets cancelled. So 1 plus y square plus x square is equal to x square plus y minus 1 the whole square. So 1 plus y square plus 2y is equal to y square minus 2y plus y. That 4y is equal to 0. Therefore y is equal to 0. Now it is purely real, and therefore it will lie on which axis? X-axis. Z lies on real axis, that is x-axis. If the modulus of z is less than 4, then iz plus 3 minus 4i so your, I would say iz plus 3 minus 4i is equal to iz plus 3 minus 4i, which will be less than, let's say, iz plus 3 minus 4i. Now this is your z, so z is modulus of z plus 5 less than 4 plus 5, that is equal to 9, because your value is given as 4, so 4 plus 5 will be 9. Answer is D. The equation not representing a circle z minus z1 upon z plus z1 is equal to 1. So z minus z1 is equal to z plus z1. Z is equal to x plus yi minus 1 is equal to x plus yi plus 1. Now this is equal to x minus 1 the whole square plus y square is equal to x plus 1 the whole square plus y square. You will open the brackets. You will get 2x is equal to 2x. When you get on this side, you get x as 0 which is on y-axis. So if x plus I beta is equal to tan inverse of z, z is equal to x plus yi, and x is a constant, then locus of z. So what you have is alpha plus beta I is equal to tan inverse of z. Now tan inverse of z can be written as x plus yi. After that, the conjugate of x plus beta is x minus beta I, tan inverse of x minus yi. When you add both the equations, you get alpha square minus beta square, or that is 2 alpha, that is equal to tan inverse of, let's say adding your 1 and equation 2. So tan inverse of A, tan inverse of B. Formula for tan inverse of A plus tan inverse of B is tan inverse of A plus B upon 1 minus AB. Two x upon 1 minus x square minus y square. So therefore 1 minus x square minus y square is equal to 2x cot 2 alpha, because tan inverse of B upon B. So what you get is x square. On the other side, when you take y square plus 2x cot 2 alpha is equal to 1. The answer is B. If log modulus of z square minus modulus of z plus 1 upon 2 plus modulus of z to the base root 3 is less than 2, the locus of z will be, okay. So z square minus z plus 1 upon 2 plus z is less than root 3 the whole square. I am writing in the exponential form. After that, z square minus z plus 1 root of 6 plus 3 z. So z square minus z plus 1 6 plus 3 modulus of z modulus of z plus 1 modulus of z. So it will lie between minus 1 and 5. If this is an imaginary cube root of unity, then the value you have to find is. So what you have to prove, you have to start with that 1 plus 2 plus 1 upon 2 plus infinity minus 1 upon 1 plus infinity. LCM for this 2, 1 upon 1 plus 2 infinity plus 1 into 1 plus minus 2 minus infinity upon 2 plus infinity 1 plus infinity. So what you get is 1 upon 1 plus 2 infinity. Basically you are taking the LCM. So here you multiply with 2 plus infinity 1 plus infinity plus minus 1 plus 2 infinity. You get 2 plus infinity and plus infinity. So what you get is 1 plus infinity plus infinity square upon 1 plus 2 infinity 1 plus infinity and 2 plus infinity. This is nothing but equal to 0. The complex plane such that the equation modulus of z plus bar z is equal to z minus z1 represents z plus bar z is equal to modulus of z minus conjugate of z. So we get z plus conjugate of z the whole square is equal to z minus bar z, that is conjugate of z is 2zz, that is conjugate of z is equal to minus 2z bar z, that is conjugate of z. So what we get is 4z z is equal to 0. So the answer is circle is passing through origin, since the coordinates have the coordinates as 0 and 0. So the answer is D. Multiplication of a complex z by I corresponds clockwise rotation of the line joining z to the origin in Argand's diagram through an angle of pi by 2. Anticlockwise rotation of the line joining z to origin in Argand's diagram, rotation of the line joining z to origin in Argand's diagram through an angle, and no rotation. So the answer is B. Anticlockwise, when you are going joining z to origin, you are going in anticlockwise direction. If cos I sin theta into cos 2 theta I sin theta till the extent cos of n theta is equal to 1, then the value of theta is, so I am splitting directly the real part and the imaginary part. Okay. So cos of n plus 1 upon 2 theta plus I sin n into n plus 1 upon 2 theta is equal to 1. When I compare, what I get is n into n plus 1 upon 2 theta of cos, that is equal to 1, and sin into n plus 1 upon 2 theta is equal to 0. So what you get is n into n plus 1 upon 2 is equal to theta, that is 2 m pi, and theta is equal to 4 m pi upon n into n plus 1, as n belongs to integers. So your answer is C, 4m pi upon n into n plus 1. 1 bi a2 plus bi till the extent, then it is equal to a square plus b square. Because here you have this a plus bi, ax square plus bn square. Squares are given, so you get your r from here, that is rk cos theta plus sin theta I, and now this your, let's say your angle is for k, so a plus a1 b1 I, a2 b2 I, till the extent a plus bi. So r1 cos theta 1 plus I sin theta 1 are 2 cos theta 2 plus I sin theta 2, that is equal to A plus BI. So R1, R2, Rn, you will get A plus BI. So when I compare, what I get is R1, R2 you get as A square plus B square, and tan for the angles will be B upon A. So you get as A square plus B square. Answer is B. Now if A1 B1I, A2 B2I, and till the extent of AN plus IBN is equal to A plus BI, the angles are given as inverse. The angles will be equal to B upon A. So the answer is C. How you get this is tan inverse of B1 upon A1 plus tan inverse of B2 upon A2. So you're defining your I till N. Next, if A1, A2 till An minus 1 are the nth roots of unity, then 1 minus A1 1 minus A2 1 minus An minus 1 equals 2. So now since x raised to n minus 1 is equal to x minus 1, x minus a1, x minus a2 till the extent of x minus a raised to n minus 1. What you get is x raised to n minus 1 upon x minus 1 is equal to x minus a1, x minus a2, x minus a raised to n minus 1. So putting x is equal to 1, you get 1 minus a1, 1 minus a2 till the extent of 1 minus an minus 1 equal to n. So the answer is 1. If it's not equal to 1, it's a cube root of equity, then 1 minus 1 minus I, 1 plus I, infinity square minus 1 minus I plus infinity minus 1, infinity square minus 1 minus 1 is equal to now as this is given in the determinant, when you solve this will be equal to 0 when you expand this determinant. Okay, so your answer is A, 0. Let Z and this components be two non-zero complex numbers such that modulus of Z is equal to modulus of infinity and argument for Z plus argument for infinity is equal to pi. Then Z is equal to, so argument of W is equal to theta and argument of Z is equal to pi minus theta, as these are both components equal to pi. So z is equal to cos theta plus I sin theta, a plus b theta. And similarly for z, I'll write as pi minus theta plus I sin pi minus theta. When you both solve these equations and when modulus is given for both, what you get is minus cos theta I sin theta is equal to minus z. The answer is D.